So we're talking today, we're starting in chapter 9. Chapter 9 is called Estimating About the Population. All right. Students don't usually have a really hard problem with this chapter in confidence intervals. It just tends to make an awful lot of sense. But what I would challenge you to do during this chapter is start to see how you can make the connections between what we've been talking about the whole semester and how we're finally applying that information to these last 2 chapters of this class. Because that's it. There's only 2 chapters left. All right, and then we're done with the semester. So we are going to start talking with a sample proportion or estimating something about the population's proportion. But either way, we're going to do it using a proportion. And remember how in chapter 8 we divided things up? We've been dividing it up, it seems like, since chapter 6. We'll start talking about either a mean or a proportion, and then we'll follow it up the next day with whatever we didn't cover. We're doing the same thing like that today. And the main reason we do that is because the formulas change ever so slightly. So we're going to tackle it one day with formulas on proportion, and then we'll tackle it another day with formulas on means. All right. So today we're talking about estimating on the population's proportion. So here is this picture, right? This is a picture of purple fan coral. It says marine scientists say that 10% of the world's reef systems have been destroyed in recent times, and that the current rates of loss, 70%, will be gone in 40 years. This is old data. I'm not so sure if that's the case anymore, because I saw something recently that the Great Barrier Reef is actually coming back. It's actually got regrowth on it, which I think is kind of interesting. Dr. Harville's lab studies corals and diseases that affect them, and on a dive along the Yucatan Peninsula, he discovered 54 of 104 sea fins sampled were infected with the disease. So I did not know this. There is a barrier reef. There is a reef that runs off of this Yucatan Peninsula, which is over there where Cancun is at, Cozumel in Mexico. And there's a reef that runs kind of parallel to Central and South America from the United States, and it goes past Belize and Honduras. And it's really cool because I didn't realize that we had that in our, over here. I always thought it was just always going to be in Australia where you had a reef like that. And this purple fan coral does grow out there. It's really pretty. I went to Belize a couple of years ago, and I'm a big snorkeler and scuba diver, and you could just see it floating there in the ocean. It's all over, and it will just kind of stay there in the water, or it'll kind of get dislodged and it'll float past you. It's really, really cool. Well, and then as another side note here, I think we're starting back up with our travels with our classes where you can do, can't think of the word all of a sudden, right? Where we do like the trip to London. I saw an advertisement for that the other day, right? Well, they have trips to Honduras, and you can get certified to scuba dive. The school is kind of part of your class. You can get the certification to scuba dive down there. And it's kind of interesting because you don't have to be a biology person to get into the class to go and do it. You could say you wanted to study, I really don't know. Maybe you want to study foreign languages or something, right? Because I was always really surprised that I was like, oh, you didn't have to just be a biology student to get to go on this trip. And yet you could still go and do this. Somehow or another, financial aid does pay for it. It can get paid through your financial aid, which I think is kind of interesting. So they're starting those things back up. If that's something that would be interesting to you, I'm pretty sure that they have them in the spring. You kind of have to get into it in the spring because the class, I believe, takes place in May or over the summer, something like that. So be on the lookout for it because I think those are kind of cool because they have a spot in Honduras in Roatan, I think, Honduras, where it's a dive spot, but it's very cool, very beautiful down there. Okay, so this guy says that he went out and he dove and he discovered 54 out of a total of 104 sea fans that he sampled were diseased. Now, the sample proportion we learned in the last class when we were talking about the probability of sample proportions, right? The sample proportion here is p hat. right? We defined p hat as being the variable of interest, the variable we're going to call this. And so in fact, in his sample, he found that approximately 51.9% of those sea coral, fan coral were diseased. So do you suppose that if I went out and was lucky enough to go on a dive where we were studying that, maybe I was down in Belize, or maybe you go on the one to Honduras, or maybe we're excited and we go to Nassau, like the Bahamas, or maybe you get to go to, Australia. We all went out and we sampled the sea fan coral. That was our task. Would we come back with 54 out of 104 sea coral that were fan coral that were diseased? Would we all come back with the same proportion? Why? Because each sample is a variable, right? We discussed that in the last class. Each sample is a variable. Okay, so we all go out and we all realize now that we're going to get a different proportion, let's say, that are going to be determined diseased. So how can I then make an inference onto the population of purple sea fan coral? How can I say, okay, well, I believe that the population of sea fan coral is diseased is roughly 51%. How can I even come up with a number if we know that our samples are all going to be different? Right? That's kind of a question to think about, right? So how will I know? When we've identified in the last chapter, we identified what they said the population was like the men's weight, right? How do they know what the average man's weight is if every time you sample, say, 100 men, the average in that weight is not going to be the same? And yet we are still making some sort of inference about the average weight of men. Same thing here. How do I know? How can I make that inference into the population of sea fan coral if I haven't gone out and looked at all of the sea fan coral that's in the ocean? That's what a confidence interval gives us today. All right. This is how we can, with confidence, with a degree of confidence, be able to say, okay, I know that I'm not going to get 51.9% of a sample is going to be diseased, but I can say with a degree of confidence, with a 95% degree of confidence, that I know that the true proportion of sea coral that is diseased is somewhere between 42 and 61.7%. Somewhere in there, right? I always think of this as it's kind of like a wiggle room, right? I know it's in there somewhere, all right? Have you ever seen those polls where they'll have a margin of error? They'll say, this is the poll that we took, but the margin of error is plus or minus 3%, let's say. Y'all ever seen that? That's the end of our confidence interval. That's what the confidence interval is giving us. 3% on the left, all the way up to 3% on the right. And somewhere in the middle is going to be the true proportion of sea fan coral that's diseased. We'll never know what that true number is because that's the whole point of inference, right? If we knew that the true number, then we wouldn't have to infer anything. So we have this interval that we're using, and that's what a confidence interval tells us. We have levels of confidence that we're going to talk about, but this is kind of the idea behind it. So some of the things that you want to make sure that you understand here, and I've got fill in the blanks for you nicely on your paper for you right there. All right, a point estimate. So the point estimate is that statistic that the doctor found, right? Dr. Holden, his statistic of 51.9% is what we call the point estimate. It's the statistic about the sample that we are using to infer onto the population. Remember your terms here. Statistic describes a sample. Parameter describes the population. So the point estimate, in this case, p hat, our point estimate is what we use to get the confidence interval that we say contains the true population parameter. All right. we have a confidence interval or an interval estimate, depending on what you look at, which is our range of values that are used to estimate the true value of the population. Okay, and again, it's based on p hat. Our margin of error is our estimate of our parameter and how accurate that point estimate truly is. All right, to find the margin of error, or in other words, our confidence interval, I should say, our confidence interval is found by taking that point estimate and adding and subtracting that margin of error. That's how we get the confidence interval. So if we're thinking, for example, of that problem that we had above, we know that we had a point estimate above of 51.9%. All right. And that becomes the middle of our interval. So just to kind of graphically illustrate this, p hat becomes the middle of our interval. We were kind of told up there, we don't really know all the information about it right now, but we know that on the lower end, our confidence interval could be at 42.1%. And on the upper end, our confidence interval was at 61.7%. So in other words, to get from the end to the middle is what we call the margin of error. Right? How do you suppose, and I'll just put this in here, it's 51.9. How do you suppose I could calculate what is the margin of error here for this? How would I calculate what that value would be? How could I find out what that distance is from the middle to the edge? What am I going to subtract? That's right. All right. Which middle? 51. Well, there's only one middle. Which edge do you want to subtract, right? All right. So I'm going to rearrange this then, and I'm going to say 61.7 minus 51.9, because subtraction is not commutative, right? I want a larger number first. That's going to give me a difference of 9.8, right? If you get a negative number, you just did it in the wrong order, all right? What if I chose to go the other way? 51.9 minus 42.1, what's that? $9.8? Okay. So in other words, the margin of error is, or the point estimate, I should say, is in the middle. It's in the middle, and the margin of error will always be the same on both sides. Now, what this says is, although Dr. Harville found a sample of sea fan coral with a proportion of 51.9% that were diseased, we're saying that, okay, although I may go out and do it, and maybe I get a sampling of 43%, and Elizabeth goes out and she gets a sampling of 55%, right? And Michael goes out and she gets a sample of 60%, right? All of those are contained within that interval, and all we're saying is that we believe that the true proportion of diseased sand coral is somewhere in there, all right? With a degree of error that's allowed. It's a tolerance, let's say, okay? So the level of confidence then is what tells me how confident I am, how much I should expect the proportion of intervals that are going to contain the parameter if a large number of different samples is obtained. This is a really kind of difficult statement to understand here. The level of confidence, we're going to look at that in just a second, but just understand that the level of confidence changes, okay? Notice, who can tell me where they may have seen this symbol before? What symbol was that? Do y'all remember? That little cursive looking X, right? That was alpha, wasn't it? Okay, and alpha is what helps us determine the level of confidence that I'm interested in. Okay, alpha helps us determine the level of confidence that I'm interested in. A couple of interpretations that we might consider here. When we think about a confidence interval, a 95% level of confidence. So 95% of the time, I'm going to capture the true population. 5% of the time, I miss it. That's what that means. 95% of the time, my confidence interval is going to capture the true population. But sampling has, in variables like that, we have errors, right? And so there are times when we may miss it, okay? And that's what our confidence level is talking about. How important is it that I capture it all the time? Or is it okay if I miss it every now and again? If I am doing a, just a regular polling, let's say, about public opinion on something, right? If I miss on something maybe innocuous, right? Something that doesn't have a whole lot of weight, let's say. If I miss the true population's feeling on something, say 5% of the time, that might be bad if I'm, that might not be always good if I'm writing a paper on it or something like that. But think in terms of if I am testing, let's say, a medical, something in like medicine or something, and we want to know with a degree of confidence how many times maybe we have positive results on this, right? Something that maybe the stakes are a little bit higher, right? I might want to capture the true population, right? A lot more than maybe if I'm just talking about a public opinion piece where I maybe don't care, right? So our confidence level can change depending upon what we're looking at, okay? And when we talk about our confidence interval, it implies that, as it says in this case, that if we had 100 different samples or 100 different confidence intervals that are constructed, we would expect 95 on a 95% confidence interval. We would expect 95 of the 100 intervals that are created to contain that true population parameter and miss it 5% of the time. Okay. Okay. Now, let's look at this example right here. This example says, in a poll in which Gallup was estimating the proportion of adult Americans who believe they're paying too much in federal income taxes, the point estimate is 0.48. So they did a sample, right? If you ever go look up Gallup or Pew sampling, remember we talked about this, maybe they talked to 1,200 people, 1,280 people probably, found out that 48% of them felt that they were paying too much in taxes. They determined that there was a 4% margin of error, right? 0.04 would be 4% margin of error, okay? They reported this as a 95% confidence interval. Those are the things that you would be looking at on a statistic. If you see any statistics given in a paper, in a research article, in a news graphic, right? They're going to throw up a percentage, but they should put the margin of error as well as the confidence interval underneath it if it's truly, those are things that you would want to look for, all right? So Gallup is 95% confident that the proportion of Americans who believe they pay too much in federal income taxes is somewhere between 44 and 52%, right? Because that's that margin of error. They sampled a certain set of people. Their sample came out as 48%. They've got a 4 plus or minus margin of error. So we're going to take 4 away from 48 or add 4 to 48. And we get this range now, right? Because if they resampled, maybe they get a different value. So what does that look like here? So this, let me put this really big here, all right? This is 100 different samples. So let's just put yourself in a scenario where you went out and you, collectively we ran an experiment, let's say 100 different times, just like y'all are gonna do when you do your activity with the M&Ms. We ran an experiment 100 different times. All right, talking about the few, same question we were asked. And all of those green lines in there represent an individual result from a sampling. All right. And each time you create, if you're doing a confidence interval, each time you sample, you create your own confidence interval, right? So notice that the vertical black line that you see there, the vertical black line is what is 0.48. It's what they believe the population parameter to be. That's what they believe the population feels about paying too much for taxes. And each one of these green lines represents an individual sample, right? So they went out and repeated this process 100 times. And let's say, because I just touched on this one right below that red line right there, there's a green dot on each of these samples that you see there. That would be the point estimate for that individual sampling that was taking place, right? So if you look here, that green dot right there indicates the point estimate for each individual sample. And then from that point estimate, everybody goes out and creates their own confidence interval, okay? So each confidence interval is going to be different, but what do you notice about all of those green confidence intervals right there? If the true population is that vertical black line, right? If that's the inference that we think is we're going to make, each one of those green horizontal lines contains that black vertical line, doesn't it? It's not in the middle. It doesn't have to be in the middle, but it does contain it. Okay? Right? That's important. This black line right here is in the confidence interval for every single one of those green samples that were taken right there. Okay? Now, what do you notice about the red confidence intervals that are listed there? They don't contain the black line, do they? They're outside. Nothing on the red horizontal line captures the black line, does it? Okay, so in other words, there were, how many black lines do you see there? 4, right? There's 4 black lines. 4 black lines, no, not black lines, sorry, colorblind here. How many red lines do you see there? How many red lines do you see?
4 red lines.
4 red lines, that's right, there's 4 red lines. Okay, so what this says is that in this simulation, there were 100 simulations done. 95 of them, 96 of them contained the true population. 4 of them did not. That's a confidence interval. We are 95% confident that in 100 samples, 95 will contain the true population and we'll miss it 5% of the time because it's an error. It's just what happens. That's what a confidence interval says. It doesn't say that that's just what it says. 95% of the time we capture it, 5% of the time we don't. And don't forget that your confidence interval doesn't mean that the true proportion is dead center in everybody's confidence interval. It just has to capture it. It just has to reach out and grab it ever so slightly for it to contain it. Okay? All right. Here are some interpretations to just make sure that you watch out for. All right. So in a different, let's say separate survey, they surveyed Pew Research surveyed 1,007 adults. Found out that 85% of them know what Twitter is. So remember, the p hat represents the sample. P hat is our sample, but we have now transitioned. We're adding a definition to it, and we are calling it a point estimate. All right. P hat is the sample proportion, but in a confidence interval, we have defined it now. We're adding to that definition. It is the point estimate. It's the point in which we are going to build our confidence interval to see if we can capture the population. Okay. So we are 95% confident that the interval from 0.828 to 872 actually does contain the true value of the population proportion. All right. We are 95% confident that it does contain it. You have to be careful in how you are interpreting it. What we really want to say is that we believe if we had 100 different samples, 95 of them would contain it, 5 of them would not. Okay. That's what we believe. I believe that this one would be knocked out because it says it actually does contain the true value. I hope that you're learning in our statistics so far that statistics language seems to really like that wiggle room, right? Watch out for things that are definite like that. It actually does contain it. Well, I don't know. Does it really? We think it's going to. It has the potential to do it. But I think I would be hesitant to say that it actually does, right? Those finite statements like that. Okay. Now, moving on, we want to talk about critical values, okay? So I'm going to define for you what these critical values are, and then you're going to add the values of these critical values to your paper in just a minute. Now, we have discussed before, and you've heard me say this term, that critical values are the value, let's say, from our horizontal axis. It's that value that separates one percentage from another percentage, okay? And in this particular case, when we talk about a critical value, we're thinking about our z-scores. Okay, so remember when we talked about z-scores that we were talking about the distance away from the center, right? The standard the number of standard deviations away from the mean that we are. And anytime we talked about a z-score, the mean was 0 and the standard deviation was 1, right? Okay. And our z-scores allowed us to level the playing field, and it allowed us to scale our values so we could compare them, right? Okay, so when we think about z-scores, we can also call a z-score that critical value, okay? So our critical value that we're interested in here, and what we're thinking of here is our z-scores for critical values is associated with that proportion of, in this particular case, alpha over 2 in the tails. Now, remember, alpha was the area, right, under the curve. The area under the curve to the right of z, wasn't it? That's how we defined it in the last class, right? Alpha was that. Now, we divided it by 2 in this case because we're talking about splitting the area between the 2 outside tails because the confidence interval is around the middle, okay? So we now have, remember, let's say if my area is 95%, then I have 5% that's not containing, right? 95 plus 5% would be 100%. So that remaining 5% that is what we would say unusual, right? We've been defining that as an unusual part. That's being split between the tails. So there's 2.5%, if that was the percent I'm using, there's 2.5% on either end. That's where that split is coming from. The whole thing still adds up to be 100. The middle is the 95% if that's what we're considering, and the outside would be split, okay? The score separating the right tail region is commonly denoted by z sub alpha over 2. It is what we typically call the critical value, and it is the value that is separating the proportions, right, or the percent. Okay, so the common critical values that you need to be writing down occur here. The common critical values have to do with the level of confidence that we're interested in. Now, most typically, we have a 90, 95, and 99% confidence interval. That's just generally what we use. That doesn't mean you can't have, for whatever reason, an 88% confidence interval or a 92% confidence interval. Standard industry is really just talking about these 3 right here. So let's start on the middle. If a confidence interval, the confidence level is at 95%, 95% of the time we capture the middle, 5% of the time we don't. That 5% is split between the tails, which is why this critical value that we're talking about is alpha over 2. Because it's alpha, which is 5% over 2, right? Now, what is the number then? Remember, our z-score is about a number off of the horizontal axis that's standardizing what we're talking about. So that number for a 95% confidence interval, or in other words, the number that is separating the outer 2.5% from the inner 95% occurs at 1.96. Look at my picture down here, right? So my z-score of 1.96 says I am 1.96 standard deviations above the mean and below the mean. And in that range, I have now captured 95% of my confidence, or 95% of the confidence intervals. The remaining 2%, 2.5% is in the tails. And it's a similar process for the 90 and the 99%. All right, think about that. If I have a 90% confidence interval, then I'm going to miss it 10% of the time, which means I have 5% on the left and 5% on the right. The z-score representing that barrier between the middle 90 and the outside 5 and 5 occurs at 1.645 standard deviations above and below the mean. Okay, this is the z-scores. These are standard ones right here. Okay. Well, that is, and this is, don't forget, this is when the mean is 0 and the standard deviation is 1, right? That's what we have when we have those. Typically, if you're running an experiment, okay, you start with this alpha, all right? Alpha is how much are you willing to miss, okay? And so when you are setting up an experiment, that's typically kind of guiding you on how much you're going to miss. How much am I willing to miss on this? And then everything as far as some of the other stuff flows from there. So it's kind of set ahead of time. It's generally not set at the end. That's where that number comes from. So this is just a practice in, all right, well, what if I wanted to find the critical value on a confidence interval that was something other than those 3 that I stated? And you do that by just recognizing, let's first sketch a picture here, just because it's easy for us to understand. We have our normal distribution. The mean of our normal distribution has to be 0 if I'm talking about a confidence interval. Standard deviation is equal to 1. So I'm looking for the critical value. Let me be clear here. I'm looking for the critical value. I'm looking for the z-score that's associated with. I want to know, what is this z-score here? I don't know. But the middle is what? What's that middle area that we're interested in right there? So that's at 88%, and I want to know, what is the z-score that is separating the middle 88% from the tails, which must contain what, 6% on the left and 6% on the right, because that would be 12. What is that value? Well, what kind of curve does this look like, first of all? What type of, tell me the shape, describe this shape for me. It's a normal shape, that's right. We know what the mean is. We know what the standard deviation is, because on a critical value, we're looking for z-scores, and that's always going to be 0s and 1s. Where do you suppose I'm going to go find out what that value is that's separating the two? All right, very good. So we're going to go to the normal calculator. You have two options there. You have the regular calculator and then you have the between calculator, don't you? Yeah, we're looking for the between, aren't we? Okay, so I'm gonna go to the calculator. I'm going to pull up the normal calculator. I'm looking for the between. And I am going to get rid of that somehow, right? I'm going to get rid of those two values that are right there because that's what I'm trying to solve for. But I know what the area is. Where does the area go? In the very far right-hand blank, right? That's my 88%, isn't it? So these should be the same number because it's symmetric around the middle. So we found that the z-score, the critical value, right? We're just kind of changing the name a little bit. Our critical value that's associated with a confidence interval of 88% occurs when the z-score is negative 1.5 and positive 1.55, right? That's all we're talking about here when we think about critical values. You'll see why that's important in just a minute. But we need to know what the critical value is as we move on in just a second to be able to determine other things. So this is just an example of, okay, well, what if it's not those three standard ones that we discussed? Okay, any questions on this? In essence, this is what you already did in chapter 7, isn't it? Normal calculator, find the critical values, find the z-score. Okay. Okay. So let's look at this example together. This should be on your paper. It says in a survey in a survey of 2019 adult Americans aged 18 or older, 1,252 of them stated that they frequently worry about their financial situation. Obtain a 90% confidence interval for the proportion of adult Americans who frequently worry about that situation. So the first thing that we need to understand is, what are we told here? We're kind of given some information in that problem. The 2019 adult Americans is what? What variable would I assign it? It's not the year. It kind of looks like it was a year, but it's not. What variable is that? It's your sample size, isn't it? Right. Your sample size here is 2019. And what is 1252? What variable would I assign it? P-hat? Is that P-hat? Not yet. P-hat has to be the proportion, but we're getting to P-hat. That's your X. So that would be your X. 1252 is going to be X. All right. P-hat then is X over N, or in other words, 1252 out of 2019. So 0.62. P-hat's got to be a proportion, okay? So you want to go through and you want to write down and see if you can identify, and I'm highly encouraging you to assign the variables to each of these values so that you know what you got and what you don't have. Next, we want to verify. What does step number 2 do for us?
See, that's going to be normally distributed.
It's determining the shape, right? It's verifying the shape for us. Remember how we talked about that last time? All right, so the NP1 minus P hat in this particular case is talking about the sample that we're looking at. Is that sample normally distributed? Okay, and as long as our formula here works out to where it's greater than or equal to 10, then we're going to be okay with it, right? We're going to be okay with it. So we would say, all right, I have 2019 times 0.62 times 1 minus 0.62. And I find out that that is equal to 475.
I think that's fair.
Huh?
I said, I think that's fair.
Definitely greater than 10. So I don't really need to know too much more about the population because my sample is actually exhibiting some sort of normal distribution. It's large enough for us to not worry about it. The point, so the next part of that, this N is less than 0.05 times capital N. What did that do for us? This is a proportion, so we had to verify independence, right? Okay, and you can't really do anything. This is the one where, okay, we have a formula to be able to calculate it, but we're talking about adult Americans. And in this particular, I don't know what the true population of adult Americans are, but I am pretty confident that 2000 is probably less than 5% of them, right? Don't you believe that 2% of these people is less than 5% of the population of adults in the America? Okay. So see, you can't always do anything with this independence thing because you don't really know what this population's size is. But there you go, we answered the question. So we have verified our normalcy, which means we can go use the normal calculator. Okay. So at this point, we choose to move to technology to be able to construct this confidence interval. All right, we're going to use StatCrunch. We're not going to calculate this by hand. So in StatCrunch, I'm now going to move to stat. Okay, so this is the first time we're using something different in a while. I'm at stat. And we're talking about proportions right now. So I'm going to move down to the proportion stat. And we only deal in this class with one sample. So we'll never choose the 2 sample option here. And now we have to decide, was this information on the proportion that I was just looking at, is it raw data or was it summarized data? It was summarized. I wasn't given a list of just raw data. So this is where we choose summary. Okay, and we're just going to fill in some blanks here. The number of successes was X, wasn't it? The number of successes was 1,252. The number of observations is our sample size of 2019. Now, we use this exact same screen for both chapters 9 and 10. Right now, we're only dealing with confidence intervals. So I'm going to go click that radio button for the confidence interval. And the only thing I'm going to change here, we're doing a 90% confidence interval. So I'm going to change it to 0.9. Everybody have, does everybody have that? Everybody was able to find that? You're pushing, you got that? Okay. So once I hit compute, we have this information here. Okay, there's a lot of stuff in that. Okay, you can see that the sample proportion is given for us, right? There's our decimal value. That's p hat. That's the sample proportion. Okay, and then the other thing that we would be interested in are the lower limit and the upper limit. The lower limit and the upper limit. Okay. The lower limit tells me that I have a confidence interval that can go as low as 0.602. And I have an upper limit that can go as high as 0.638. All right, everybody write those numbers down if you haven't already. I'm going to change my screen here. Okay. So important to understand that our lower limit and our upper limit. So StatCrunch just spit out for us automatically the confidence interval. I do want to make sure we understand that the sample proportion represents p hat. So the confidence interval that I would be interested in says 0.602 all the way up to 0.638 is the confidence interval. So we're 95% confident that the proportion of adult Americans who worry about their financial situation is between 0.602 and 0.639. That's how you interpret the confidence interval. We are 95% confident, 90% confident that the proportion of adult Americans who worry about their financial situation is somewhere between these two values. That means that in 100 samples, 90% of them would capture the true population, 10% of them would miss it. Now, what if I wanted to ask you, what is the margin of error? Okay. Sometimes it helps to draw a picture. Maybe, maybe not. What we have going on here is, remember that the point estimate is in the middle. The point estimate is in the middle. And the point estimate was at 0.62. The upper limit was at 0.638. The lower limit was at 0.602. So what I want to know is, what is my margin of error? What is the distance to get from the middle to the edge? And just like Michaela told us before, right, you're just going to subtract to get that distance, the edge from the middle, whichever way you want to go. So we found that the margin of error is roughly, we'll call it 2%. So our point estimate, we would say that 62%, that's our point estimate, right? This is us inferring to the population. We believe that 62% of adult Americans worry about their financial situation with a margin of error of 2%, plus or minus 2%. And we have a 90% confidence in that interval, okay? Okay. Now, I want you to go in and I want you to calculate for me just real fast, and then I want you to write it down, okay? I want you to go back in and calculate using this exact same scenario here. I want you to calculate both the 95 and the 99% confidence intervals. And all you have to do is go back into options here, edit, and change the confidence interval down there. Please write down for me what intervals you get. And then I want you to calculate the margin of error for me on those. All right. So you're calculating a 95% and a 99% confidence interval. Remember that your interval comes from StatCrunch. It comes from the lower limit and then the upper limit. And I would like for you to calculate the margin of error in each of those cases. Somebody tell me, what was your lower and upper limit for your 95% confidence interval? The 3 decimal places.
599.
Okay. And what's the margin of error on that? Did you go from the left to the right, all the way from the left to the right? That would be double. Okay, 0.021, right? Okay. And what about our 99% confidence interval? What's the left margin? What's the lower limit? What's the upper limit? And what's the margin of error? Okay. What do you see happening here as we increased our confidence level? Confidence interval, confidence level, confidence interval. That's what I want to say. What do you see happening as we increased our confidence interval? We started out with a 90% confidence interval. And as we were increasing it, what's happening? The margin of error increases and our interval width increases, right? Okay. So as I increase the confidence interval, I'm increasing the size of the interval, right? As I increase my confidence level, I am increasing the interval size. Why do you think that makes sense? How many of them do I capture on a 90% confidence interval? How many confidence intervals capture the true proportion, the true population? Out of 100. On a 90% confidence interval. 90 catch it and we miss 10, right? Okay. So in a 95% confidence interval, how many catch it? And we miss what? Okay, so now I'm only willing to miss 5 out of 100. So maybe I need to make my interval a little larger so that I can capture more, right? I got to capture more. Think about that. Now I'm going up to a 99% confidence interval. How many do I miss? 1. I can only miss 1 out of 100, right? So now I really need to make that interval much larger so that I can capture, I'm more likely to capture the 99 I need because I can only miss 1. You see how we're increasing the interval as we increase our confidence level. It has to do with how much error are we willing to have. I don't want a lot of error in a 99% confidence interval, right? I want to capture 99 out of 100. Okay, in a 90% confidence interval, I'm all right with missing 10 of them. Okay, so to capture more, I have to have a larger interval to be able to capture more. Okay, sometimes that doesn't always make a lot of sense, but that's how we're finding it. Okay, so as I increase that confidence interval, as I increase my level of confidence that I'm interested in, it's going to increase the width of my confidence interval. Okay. Now here is the formula that we would use to find our margin of error should I decide to calculate it by hand. Okay, notice what's in this formula. So E is standing for, this capital E stands for the margin of error. If I wanted to know what the margin of error was, okay, I could calculate it by hand. Notice that this Z sub alpha over 2 was our critical value for the confidence interval we were interested in. Remember those, you wrote them down, right? Z sub alpha over 2 was the critical value related to the confidence interval we were interested in. And then we're multiplying it by P hat 1 minus P hat over N. Does anybody recognize what that square root, what that is? What did you say?
Standard deviation.
Exactly, that's the standard deviation of our sample, isn't it? So this kind of makes sense then, right? That margin of error is going to be calculated by multiplying the critical value by the standard deviation. Okay, so how many standard deviations away from the middle am I, in other words? We're standardizing it, aren't we? Basically, that's all this is doing. Now to calculate this by hand, we want to suppose, and I think I have this problem for y'all, don't I, on your paper? Okay, suppose that the number of individuals surveyed is increased fourfold. In other words, we're still talking about that same problem from above, but now we want to increase the sample size to talking to 8,076 people. Okay, but the proportion that still believed it is going to stay the same. Okay, I want to compute the margin of error then on that confidence interval. In other words, what we're trying to see here is we want to determine how does the size of my sample impact the margin of error this time. So let's write down some of the new information that we have. We know that 8,076 becomes our new sample size. We know that P hat is still going to be 0.62. So we're still maintaining that 62% of the population are worried about their financial income. We just want to know what happens to that margin of error as I increase the sample size. On a 90% confidence interval, right? So for a 90% confidence interval, the critical value was what?
Critical value is 1.645.
Good, 1.645. That's our critical value. Right? That's this value right here. That's the critical value. So now it's just a matter of plugging these values in to your formula. What is the margin of error for a sample of 8,072 if we have these numbers here? 1.645 times 0.62 times 1 minus 0.62, which is 0.38, divided by the 8,076. Okay, in your calculators, you've got to do order of operations here, all right? So start underneath the square root symbol first. Start underneath the square root symbol first. Do the multiplication and division. Then work your way out. Then we do the square root Then we do another multiplication times the 1.645. So I want to know to 3 decimal places what the margin of error here is. To start underneath the radical symbol, underneath the square root symbol. Eric, you went to the Spy Museum. You went to the Spy Museum. We spent 4 hours there. Hey, do you have a number?
Zeros, 8, 9.
All right. 0.009 if we round it to 3 decimal places. What was the margin of error that we found above for our sample size of 2019?
For the 90%.
It was 0.018, wasn't it? Okay. So what happened to the margin of error as I increased my sample size? We went from 0.18 or 0.18, we'll call it 1.8% to 0.9%. What happened? Did it get larger or smaller as I increased the size of the sample? Does that make sense? Why? Why does it make sense? Right? So when you're increasing the size of your sample, you have less error, don't you? Because you have more repetition, right? You've got more, you have less variability. When you increase your sample size, you talk to more people, meaning you would have less variability, right? So you have less error. So your margin of error decreases. So these are in contradiction to each other. As I increase the sample size, the margin of error decreases. As I increase the confidence interval, the margin of error increases. Make sure you understand the differences between those two, right? As I'm increasing my confidence interval, the margin of error must grow because I have to capture more of them. But if I increase the number of people or the value of my sample size, the variability decreases, so the margin of error actually gets smaller. Okay. Now there is a sweet spot here, right? They went from talking to 2,000 people to talking to 8,000 people. That's not always an option, right? That's not always something that is something that you can do. So just to reemphasize, increasing the level of confidence means that we increase the width of the interval and we increase the margin of error. If we increase the sample size, we decrease the margin of error. Okay. So what's the sweet spot for the sampling, right? What's our target number to be able to gain a sample that's large enough for me to have a confidence in it, right? That I have met the requirements that I want, but not overboard, right? And this is where we have these ideas right here. Do write these formulas down in case you're asked to do this by hand for whatever reason. But again, on this one, to determine the sample size, we're actually going to be using StatCrunch. But the two formulas that you could use here are given in the middle, right? So the very first formula, and everything in there is if I was calculating this by hand. Your point estimate that you're trying to go for times, so the number of success, the proportion of successes times the proportion of failures. times that critical value divided by the margin of error that we want to maintain squared. We're working backwards. Remember how I told you that you initially start with your alpha. So if I know what my alpha is going to be, if I am aware of what, let's say a previous point estimate was, and I know within what margin of error do I want to maintain in a particular confidence interval, then I can figure out, okay, well, what should my sample size be? The second formula down there is, all right, well, if I don't have a prior point estimate, like if this is brand new research and you don't have anything already out there that says something, then you would just use this other one here, the 0.25 times the critical value over the margin of error squared. And just to be clear that whenever we have a normality condition that is not met, the proportion of intervals that capture the parameter falls below the level of confidence. In other words, things start to break down. All right, we kind of saw how our formulas didn't work when we did that in chapter 7. And this is why it's important for us to check that normality. So in other words, if your normality condition is not met, if your NP1 minus P is not greater than or equal to 10, which it could happen on your M&M's thing, then to eliminate that error that could occur, you just increase the sample size, okay? That's a way to work around it. All right, so this says that we have a social worker who wants to know the proportion of the U.S. population over 16 who provide elder care, which is unpaid care for someone with a condition related to aging. What sample size should be obtained if the social worker wants to maintain or estimate within a 3 percentage points of the true proportion with a 95% confidence? Let's first work this by hand and prove it to ourselves that we know how to do it, and then we'll go check our answers with Stackbridge, all right? So to work this by hand, we need to use those formulas from above, but what we want to identify are, we want to know what is P hat, what is the prior point estimate. In question A, it says the social worker uses the 2015 estimate of 16%. So there's your prior point estimate. We need to know what Z sub alpha over 2 is. In other words, what's the critical value? What is our confidence interval that we're looking at here? What confidence interval does she want to use? 95%. And what is Z? What is the critical value for 95% confidence interval? 1.96. And what is the margin of error that she's interested in maintaining? 3 percentage points. That's right. So the 3 percentage points, she's talking about 3%, but we want to change it to 0.03 for our formula. So the sample size is equal to 0.16, because that's P hat, times 1 minus 0.16, times the 1.96 divided by 0.03 squared. Remember, order of operations, start with exponents first. So do the division. 1.96 divided by 0.03, then square it. and do your multiplication. With sample sizes, you should round up to your nearest integer. Does everybody get 574? $574? I only have one person that has acknowledged that they got 574. Did you all get 574? Addison, did you get it? Okay, Michaela, you didn't get it either. Start with this. Do 1.96 divided by 0.03. Enter, or whatever. Now square it. You know where the square button is? Or did you round up?
Well, it's 573.08. So.
You gotta round up. So it's automatic
No
round
matter
up.
what, just
No matter
round
what,
up.
round up. Okay, Addison, are you at the squaring part, right? Okay, so just ladies, 1 minus 0.16, so that would be 84, all right, 0.84. So I want you to now multiply 0.16 times 0.84. You get 574 if you round up now. Yeah. Okay. All right. What if she has no prior estimate? Part B says, what if you've got no prior estimate? That formula looks like n is equal to 0.25 times 1.96 divided by 0.03 squared. Round it up again. So always start with your division, which is inside of the parentheses, inside of the exponent first. Okay, do you get 1068? $1.96 divided by 0.03 squared times 0.25. You get 1068? Got to round up.
There you go.
Start with this stuff right here. No, just divided by. Yeah. Now square it. And now multiply. 1068. You gotta round up. You always gotta round up. Okay? Does everybody get 1068 when you round up? So look what happens. What was the size of the sample that they needed if she had the prior estimate? Still wanting to maintain a confidence interval of 95% and a 3% margin of error. She only had to talk to 574 people, right? With no prior estimate, it pretty much doubles it, doesn't it? Okay, and how do I do this using StatCrunch? You still need to identify these components that we did, that we wrote down, right? The p-hat, the prior estimate, you need to identify your margin of error as well as your confidence interval. So I'm going to go back to the StatCrunch. We're dealing with proportions today. So I go stat, proportion stats, one sample. Here, if I want to know the confidence interval, I'm going to choose the width sample size, the very bottom option right there. Okay, so there's some things we have to put in here. She wanted a 95%, was it 90 or 95? Yeah, it was 95, right? She wanted a 95% confidence interval. Her prior estimate is 0.16, right? P hat is 0.16. I'm putting that in the target proportion. This is where the width is going to be different. I want everybody to make sure you understand. The width I'm fixing to put in here is the total width, not just a single, not half of it, right? The margin of error is from the midpoint to the edge. They want the width, the actual width of my confidence interval. So double your margin of error. That's all you have to do, double your margin of error. So it's not 0.03, it would be 0.06. So you're going to double your margin of error because it's 3% on the left plus 3% on the right. You hit enter and you get 574. Okay? That's how you do it with a prior estimate. The only thing that changes is that second question on our, that second question that says, okay, well, what if she doesn't have a prior estimate, right? What if she doesn't have a P hat? If you look at the technology help for StatCrunch, because you'll probably forget this, but it'll tell you in there that for the target proportion, inner 0.5 is no prior estimate exists. So we just put 0.5 here. And we get the times 68. So if you forget, when you go to the helps on your homework, all right, just click for the StatCrunch help on the problems here, okay? But that's how you calculate it using the StatCrunch calculator. Now, really quickly before you leave, all right, I would like for you to complete the individual portion of your confidence interval for your box of M&Ms. This is going to be a quiz grade. Go to the store and buy a box of M&Ms. All right. Does it say in there? I'm looking really fast. So Mars at one point said that 20% of their 20%.
Number 4.
Yeah, there's this number 4. Mars claims that 20% of their boxes should contain orange M&Ms. You're trying to determine whether or not. So what we're doing is our box is its own sample. All right, so you need to go through and count up all of the, count them up for me, or count them up and figure out what proportion of your box contains orange M&Ms. Okay, and if you would do me a favor, would you please just write down, I'm collecting data, I've been doing it now for probably 6 years. I'm collecting the data on all of the colors. Can you just write down, just record all the colors for me? But this is only interested in the proportion of oranges, okay? Construct a 95% confidence interval around your point estimate. And then we'll see how many of our boxes contain the true proportion that Mars claims. All right? All right, y'all have a good day, and I'll see you back here on Wednesday.
When is it due?
At the beginning of class. Yes.